Hello everyone and welcome back to Nunley Math. I'm your host Aaron Nunley. Thank you so much for joining me here today as we continue our discussion of ratios, proportions, and proportional relationships. In our previous video, we talked about how proportions can be used in geometry when working with something referred to as similar figures. So if you have not already watched that lesson, I'm going to encourage you to go back and take a look at that lesson before you watch this one, because this one is very, very dependent upon that lesson. In that lesson, we said that similar figures are figures that have the same shape but different sizes. And we said there were two ways to check and see if geometric figures were similar. We said that they have to have corresponding angles that are congruent and corresponding sides that are proportional. If that is unfamiliar to you, then you might want to go back and watch our lesson on similar figures. For now, what we're going to do is we're going to solve some problems involving similar figures with a focus on something referred to as indirect measurement. Now that last video got a little out of hand, got a little bit long, so I'm going to try and keep this one just a little bit shorter, so we're going to move right into this here today. Indirect measurement is when we use similar triangles to measure objects indirectly. We use similar triangles to measure objects indirectly. For example, suppose I'm walking down the street and I see a lamppost. I'm like, wow, I wish I knew how tall that lamppost was. But I look at it and I can see, hey, this lamppost is way too tall for me to just grab a tape measure or a ruler and measure. Maybe it's higher than I can reach and I don't have a step stool, or maybe I don't actually have a measurement device with me that's reasonably long. There's a lot of reasons why I might not be able to measure that lamppost. Perhaps I just don't want anybody looking at me funny, being like, hey, why is that dude climbing the lamppost? Regardless, I don't want to have to measure this in a traditional way with a tape measure or ruler. But perhaps as I'm standing next to the lamppost, I realize that the sun up in the sky is casting a shadow from my body down on the ground. And that shadow is not terribly long. Maybe the shadow is about 3 feet long. If we think about the sun being up in the sky and its rays shining on us, if we're standing reasonably close to the lamppost, then the sun is going to shine down on us at angles that are the same as they are over in the lamppost. And that's really the big idea behind what we're doing here. If I were to take my height and I were to think of it as one side of a triangle and my shadow as another side of a triangle, and I could draw a line between my head and my shadow's head, I would be able to create a triangle, and then I could do the same with the lamp post. Hopefully you can see those triangles now. I know these triangles are going to be similar because if I'm standing straight up and if the lamppost is standing straight up, then I know this is roughly a 90-degree angle. If the sun is in the same spot and we're reasonably close together, it's going to shine down here and it's going to cast a shadow at roughly the same angle. And if I know two angles in a triangle, and I know triangles have 180 degrees, then I know the third angle must be the same as well. If all the corresponding angles are congruent, then this will be a similar set of triangles. Once I know that they're similar, then I know that the ratio between this triangle, or corresponding sides of this triangle, is going to match the ratio of the corresponding sides of the lamppost triangle. Now notice that I have triangle ABC here, and I have triangle DEF here. ABC being the lamppost, and DEF being the person, or in this case, myself. Here's what I need to do. Just like in the previous video on working with similar triangles, I'm just going to match up which pair of items I'm given that matches the lamp post to me. When I look at this, because I know where the sun is and I know that these are my shadows, I know that the shadow lengths are going to be one pair of corresponding sides. So I have 7.5 feet to 3 feet. That's the lengths of our shadows. Our shadows are given to us. But I know the height of myself, but not the height of the lamppost. Because of that, I'm going to plug in the 5 on the bottom because triangle DEF is the triangle that relates to me. This is my shadow, this is me. This is the lamppost shadow, and this is the lamppost. It's the unknown. You've already done the hardest part of the problem because once you have this set up as a proportion, the means extremes property tells us how we can solve it. I'm going to take the 7.5 times the 5, and I'm going to take the 3 times the x. If you're unfamiliar with the means extremes property, then you need to go back and watch our lesson on proportions. Once you've done that, we're going to simplify this just a little bit. 3 times x is 3x. 7.5 times 5 is 37.5. And then to get rid of a times 3, I'm going to multiply both sides by the reciprocal. Remember that multiplying by the reciprocal is the same as dividing both sides by 3. It was just easier to type it as the times 1/3, leaving you with just x equals 12.5. So if I know these are similar triangles, then I know the lamppost must be 12.5 feet tall. What you've seen here is really everything that we're going to be talking about in this lesson today. The rest of what we're doing are just some different examples that might have the information presented slightly differently, but in every single case you're going to be using a proportion to find the missing side of a similar triangle created using shadows or some other form of similar triangle. Here's another one for you. A tree in front of Marcel's house has a shadow that is 12 feet long. Marcel's shadow is 3 feet long. If Marcel is 5.5 feet tall, how tall is the tree? If you feel comfortable, I would suggest pausing the video, trying this on your own, and then skimming ahead to see if what you get matches what I get. If you're feeling uncomfortable, I would suggest that you start off by trying to draw the triangles separately from one another. Notice that right here, you have a large triangle for the tree and its shadow. You have a small triangle for Marcel and his shadow. Some people find it a lot easier to draw the tree triangle and Marcel's triangle separately. If you don't need to do that, certainly don't feel obligated to do that, but it might be helpful. As is the case every time we do a proportional relationship, you need to find out what is given to you. So we're going to look at Marcel and the tree. You're going to look at the shadows, and you're going to see which piece of information you have both of. Hopefully you realize that you have the tree's shadow and you have Marcel's shadow, so you can fill that in as 12 and 3. That means that we're looking for the tree's height compared to Marcel's height, and you get h over 5.5. Remember, the tree can be on bottom and Marcel can be on top if you like, but what is important is that you make sure that the shadows stay together, the actual objects stay together, and you want to make sure that the tree is always on the same spot or the same location. If it's on the top, they all need to be on top. If it's on the bottom, they all need to be on bottom. This is the hardest part of the problem because everything else is just the means extremes property, which hopefully you're getting really good at. You cross multiply the 12 and the 5.5 and the 3 and the h. You simplify, multiply both sides by the reciprocal, and you come up with the height of the tree is 22 feet. It's not bad, right? Hopefully you didn't have too much trouble with that. I'm going to give you another one of these. I'm going to strongly suggest that you try this on your own. I'm going to start doing these faster and faster. Don't forget, you may find it easier if you take the flagpole and its shadow and draw it separately from Jason and his shadow. The problem says his shadow is 10 feet long. The flagpole shadow is 40 feet long. If the flagpole is 20 feet tall, how tall is Jason? We have different pieces of information this time, but we're still comparing a flagpole to a person. Are we given the people and the flag, or the person and the flagpole, or are you given the shadows? Well, hopefully you realize that you are still being given the shadows, 40 to 10. And hopefully you realize the only difference is this time you're given the flagpole and you're solving for Jason's height. Flagpole is on top, so that's 20, and the x goes on bottom. Again, we're going to use cross products or the means extremes property to multiply this together. Simplify, multiply both sides by the reciprocal. Again, some people find it easier instead to just divide by 40. I am comfortable with that if that's how you'd like to do it. And you end up with a flagpole, or with Jason being 5 feet tall. You can see I've got a little typo there that I'm going to have to go and fix. That's a cut and paste from the previous slide. We know that the Jason, oh that's funny, we know that Jason is 5 feet tall. Not too bad? Hopefully not. Again, here is going to be another example. You might want to pause this and try it on your own. It does look a little bit different, so I am going to walk through this one slowly as well. This is a surveyor problem. A surveyor wants to find the distance across the lake, but she cannot measure it directly. It's too big. Think about that. You can't really draw a tape measure across a long lake. It's inconvenient at best, and depending on how long your tape measure is, it might be impossible. So she decides to use similar figures to find the measure, find the distance across the lake. Remember that triangle THE is similar to triangle LKE, so we set up our proportion. This one does not use shadows. Instead, it uses a technique that surveyors actually use when measuring distances in real life. They set up an object on the ground, maybe a stake or something like that, and then they step back and they create a known measurement, and they take measurements from 2 or 3 different locations. So they would measure from here to here, and they would measure from here to here. And then they would take a measurement from here to the corner and here to the corner. And by knowing by sighting through a little, it's almost like a little telescope, by sighting the distance here and measuring, and then sighting the distance here and measuring, and doing the same on the other side, they can use those given measurements to create similar triangles. Now I'm going to erase all that ink because it's getting kind of messy and it's kind of in my way. Again, you're going to fill in the pieces of information. The tricky part here is seeing what matches to what. But in our last video, we said that we can use the location of the letters in the names to see what matches. For example, this 1.5 is TE. So I come over here and I say, oh, there's TE. That has to match to LE. LE. Notice my little L got clicked off. I'm not sure why that L's not there. This 1.5 matches to this 2.4. Notice that HE, I'm going to switch my colors. Let's switch to blue. HE, that's this piece right here, is the last 2 letters. That has to match to KE. So HE matches to 2.6. And then finally, let me switch colors one more time. And finally, the TH, the first 2 letters, matches to LK, which is right here. So when I look at my pairs, I know the 2.6, but I don't know what 2.6 matches to, so that's not helpful. I know the 1.5 matches to the 2.4, and so that's what I'm going to use as my measurements. Once again, you may find it helpful to draw the figures separately. I don't always do that, but certainly it is something that you can do if you're having trouble seeing it. The important thing is to realize that the 1.5 matches to the 2.4. The other thing we know is we're trying to find the measure of LK, so we have to fit that in. LK is on the bottom, and then we need to know what LK matches to. LK, we said, matched to the 1.7, and you've done the hardest part of the problem. Again, I'm going to get rid of all this extra ink. I'm going to go quickly through this. You can pause the video if you need time to write it down. We're going to cross multiply with the means extremes property, simplify, multiply both sides by the reciprocal. You might feel more comfortable just dividing both sides by 1.5. The effect is the same. You end up with 2.72. So the lake is 2.72 kilometers wide. How about this one? Again, try this on your own. Make sure you're using the congruence symbols to help you match things up. You can redraw it if you need to, where you can see each piece separately and you can spin them around to right directions. That's entirely up to you. I'm going to do this one a whole lot faster. I happen to notice that in ABC, from the right angle to the 1 tick mark is 60. So I come over here and I see my right angle and 1 tick mark. It matches to 20. So I'm going to say 60 matches to 20. And then I know I need to get D. D is going to be down here. That's what I'm trying to find out. It's from the right angle to the 2 tick marks. Right angle to the 2 tick marks is 48. And now you can use your means extremes property to work it out. The stream is 60 meters wide. Sometimes students ask me, Mr. Early, can we take 60 over 20 and simplify that to just 3 over 1 so we have easier numbers to work with? Absolutely you can. If you cross multiply that, you get 3 times D equals 1 times 48. And then you just divide both sides by the 3 or multiply by the reciprocal. You're also going to get 16. So feel free to simplify if having smaller numbers is going to be helpful to you. I have one last example. Again, I'm going to recommend that you try this on your own. If you need to draw the triangles, please take the time to do that. It might be useful to you. Make sure you use the little symbols to guide you in determining what matches up. I happen to know that the right angle to 1 is 20 feet. The right angle to 1 right here is 5 feet, so that is given to me. Again, that would simplify if you really wanted to. I know I need to find D, and I know that D goes from the right angle to the 2. Also from the right angle to the 2 on the big triangle is the 28, and there you go. I'm going to do this a lot faster because this is just computational. Notice that I do have a little typo here that I need to go back and fix. That should be a 20. So 1/20th on each side gives me a 7. The stream is 7 feet across. Hopefully that was a lot faster for you this time. I did this quickly because once we understand similar figures, using it for indirect measurement is not a huge leap in logic, so hopefully this went very, very smoothly for you. If you did have trouble with that, I would recommend going back and watching that similar figures video, but I think this is going to fit real nicely into your understanding and what you already feel really strongly about, feel really well about. So thank you so much again for watching. I do wish you all the very, very best of luck. You all take care of yourselves, all right? Bye-bye.